And it's now my pleasure to announce Julian Petzold, who ends our session with talking about plants again. So long time we didn't hear about plants, and now we get a model of robots and plants. Looking forward to it. Thank you.
Thank you.
Stage is yours.
Thank you. Let me just share my screen. You can see the slides?
Yeah, it works.
Perfect, thank you. Yeah, so my talk has the title of A Concept of Full Plant Morphology Modeling for Robot Plant Biohybrids. This is something Mostafa, Wahby, me and Heiko Hamann are working on right now. This is a little bit of a continuation of one of the tracks of the EU Horizon 2020 project, Flora Robotica, which ran from 2015 to 2019. In Flora Robotica, the target was to build biohybrid systems that are a symbiosis of robots and plants. These biohybrid systems are supposed to generate architectural artifacts. So this is a merger of buildings and plants. And so why would we want to do this? Plants are being used as a reasonably durable, low energy, low environmental impact material for building since basically forever, because wood is plant material. But maybe it's better to keep the plants alive and let them do the work. So you can see here on the example of a living root bridge on the right, where people, the people living there, regularly and carefully braid these roots over this river. That there are some advantages to using living material rather than dead matter. So one of the main advantages might be durability. If you imagine a metal or wooden bridge in this kind of jungle-like environment where you have a very high humidity, high temperature, then the bridge would probably rot or decay. But these bridges actually grow stronger over time because the roots still grow. So we also can adapt, these plants can adapt to impacts from the environment. And what's very useful is also that there is very low energy expenditure on the side of the designer of the system, because you only have to tell the plant where to grow, but the growth itself is done by the plant, the generation of the material. Sorry. Okay. So in previous work, we during Flora Robotica, we had a model of plant growth for a bean plant, which used a representation using a 10-point plant stem vector. But we wanted to change that a little bit because the representation was not scalable enough for large plants and did not support branching. So what we want to do is we want to model plant growth using full plant morphology, using the full plant morphology. So what we have here is the already existing or not yet existing full toolchain, and we have it in simulation and online, so in reality, with lights to control the growth of the plant and a camera to get feedback from the plant back to the system. This was already set up in some way before, but what we want to change is on the bottom, there we see a VAE and grayed out an LSTM. This was previously represented by the 10 stem point vector and an LSTM for modeling the temporal dynamics of the plant. But we want to replace the 10 stem points by the variational autoencoder representation using the autoencoder's latent vector. And the next step that we will be doing is we will get temporal modeling by training a new LSTM based on the new representation of the plant. So we hope that the new model representation will support bifurcating plants, which would be a good step forward for generating complex architectural artifacts, such as chairs or meshes for canopies and buildings. Furthermore, there was a size limit for the 10-point stem vector of the plant, so we hope that we can model larger plants as well. So what we're using is the common bean plant, Phaseolus vulgaris. Why do we use this plant? Because it has quite some advantages. It grows very fast. It has a very fast motion. It's actually quite well known and common, so it's easy to get. It's easy to cultivate, so you can easily set up experiments, and it can display complex behaviors. It has a good response to certain stimuli, and what we're using is phototropism, which is the directed growth of a plant towards a light source. And by manipulating these light sources, we can in turn manipulate the growth of the plant. So our work foots on the toolchain that was developed in the paper "A Robot to Shape Your Natural Plant" by Wahby et al. And I will go through this toolchain and talk about the most important steps and what we changed. So our focus, what we will be changing, what we did change, was the data collection and representation method. So previously it was the 10-point stem vector, and we are replacing it with the latent vector of a variational autoencoder. But first, let's quickly go through the toolchain from top to bottom to contextualize what we've done. So here we can see that we have a data collection setup. Oh, I'm sorry. Where we took pictures of growing bean plants that consisted of a grow box with a black background, then a flashlight for taking pictures. So this way we can isolate external light sources from the experiments. And the flashlight is only on for a very short amount of time to not influence the growth of the plants. It's only for recording data. Then marked with 3, we have 2 robots as light sources. These are for controlling the growth direction of the bean. 4 is the plant itself, and on the opposite side of the grow box, we have the camera and controller that record the experiments and control them. So the lights are a simple binary decision. Either the left light can be turned on or the right light. So in the previous work, data was collected using 6 experiments. From these experiments, 5,000 images were captured. And these images were augmented with classic data augmentation methods to generate over 100,000 samples of stem point vectors of bean plants. So let's talk about the stem point vector. I will go over this quickly because it's part of the previous work that we're replacing now. But basically what was done was that the image was prepared by cropping it and removing the background so that only the bean stem is remaining. This was done using a green channel selection. And then the anchor of the plant was defined. The anchor is actually predefined because it's always, because the plant pots with the freshly grown beans were always placed in the same position. So this was predefined. And then the plant tip is basically the furthest out green point that's in the image. The 10 stem points were then fit into the plant in between the anchor and the plant tip and onto the green areas. So, but this was only a representation of the plant. The next step, of course, which is interesting because we want to steer the The growth of the plant are the temporal dynamics of the plant growth. And then, of course, having a controller that then controls the growth of the plant. So Wahby et al. Used Keras in TensorFlow to train a long short-term memory network of the plant stem geometry vectors, such that it can be used to predict the geometry of the plant in the next time step, according to the light settings. So at each time step, they use this to input the current plant stem description, an obstacle description, because the task for growing the plant was to grow around an obstacle, and a target for the bean plant's tip to grow to the controller, which is here on the bottom. And then the binary output of the controller defines the light conditions of the next step. The new light setting with the current plant stem was used as an input to the LSTM network to predict the response of the plant to the new light setting. This controller on the bottom was generated using neat, so it was evolved. As you can see here, this worked. You can see that the plants reach the target area and avoid the gray obstacle area. So why did we want to change this? So we wanted to change our model because we had certain restrictions regarding the branching of the plant and the maximum height of a plant that can be modeled with this approach. So we want to change this model and replace it with a variational autoencoder. Here we use the feature vector of the variational autoencoder instead of the 10 stem points to represent the bean plant. So in a variational autoencoder, a high dimensional image, so the high dimensional image input data is encoded to a lower given dimensionality. And then using a decoder, it is decoded back to the higher dimensionality. So we have an input and a reconstructed input. And there's probably going to be some loss between X and the reconstructed X. And this loss is minimized to achieve a lower dimensional representation of the original data, here marked as Z, the latent vector, with as little loss of information as possible. So we are actually interested in this latent vector Z, not in the reconstructed image X, because it represents the most relevant information of the input, but encoded in a very compact way. So what we have here is we have over 12,000 bean plant images, which were scaled to 64 by 64 pixels. And these were RGB images. So we had a dimensionality in the low 10,000s. And this data was then broken down to the latent vector, which only had 50 data points. So it only had 50 dimensions, sorry. And then reconstructed to the over 10,000 dimensions. So we did this using a convolutional variational autoencoder. For this, we had 4 convolutional layers per encoder or decoder. We used a stride of 2 pixels, and we used ReLU activation functions everywhere, but in the final output layer, where we used a sigmoid activation function that moves the output to the interval of 0 to 1. The loss was the mean square error between the original image and the reconstructed image. And we trained 50 epochs with batches of 100 images and achieved a loss of 5.68. So this is our result. Here you can see that, of course, there is some loss of fine detail, but all important information is still present. We can see the tip of the plant, and we can see small branches emerging near the top of the plant. So we have a full plant morphology representation. We should not be restricted anymore to 20 centimeters of plant growth. And we should also be able to represent branching, as you could see a little bit with the dots, with the green dots near the top of the plant. So, but why do we do this? So this is a representation, but no temporal model yet. So we cannot model growth yet. We can only take an image and represent it again. But in our production system, we actually don't need the reconstructed representation. We don't need the decoder. We only use the latent vector. So we will use this latent vector as an LSTM input, for example. And this LSTM will then simulate our temporal dynamics. And we do this because for an LSTM, the prediction of the task of predicting the next time step of a plant's growth would be quite difficult to do if we use the large 64 by 64 pixel RGB images as inputs, and we would not expect good results. But with a smaller 50-dimensional latent vector, we are hopeful that we will predict the next time step of the plant's growth configuration. So, of course, this opens up some future challenges, but also opportunities. First of all, the 50-dimensional latent vector is still a lot more data than the 10 stem point vector of the plant. So it might still be a bit too much for the LSTM. So we might have to replace the LSTM. This could, for example, be done using a recurrent highway network. But it also offers some opportunities, because we could enhance the plant representation by looking at the latent vector and eliminating certain image features that do not correspond to growth relevant plant features. For example, some shading in the background that we do not actually care for. So, and in the end, we hope that the full plant morphology representation will allow for controlling bigger plants, and that we can model branching plants, for example, for braid-like structures in buildings that might be relevant for attaching further things to. I think this is it. Thank you for your attention.
Thank you, Julian. Please give questions in the chat while people write into the chat. Let me ask one question, please. I think when you showed that picture where you had this gray bar, the plant needed to grow first away and then get a little bit stiff and then grow further. So how is this change of the properties of the stem? Is this also something that can be learned this way, or is this something that you have to put in a priori knowledge about that?
So I guess this would be the stem stiffening, if I understand that correctly.
Yeah. Can that the plants first, they start very soft and green, and then like if you look at a tree, then you have this wooden, and that's the very extreme now. But they change their physical properties at the base while it's still growing further up. And can this also be like part of the process to create such a model for these processes, or?
I think this could be learned by the temporal part of the system. So in this case, that would be the LSTM, maybe based on the spacing, like in this case, based on the spacing of the vector, or maybe in the VAE representation based on the color of the plant. But yeah, I think there's no there was no special consideration for this stiffening.
Yeah, because you said like you can bring this to larger plants and branching, and at some point then physics and how stiff, how robust that is, how much it can carry before it bends, all of that will play a role then if you scale this up to a larger level. So this is why I'm asking.
So
Yes.
maybe I can follow up like a little bit here. So the video that we see here is from our previous work, and we actually so that the LSTM network, as Julian said, could already learn something about the stiffening. So for example, here we had this obstacle that is like represented in this gray object. And if you can you play the video, Julian, please?
Good to see you, Mostafa.
Yeah, good to see you too.
Long time.
True. Yeah, so the controller here basically learns so it wants to achieve to reach the target, to steer the plant towards the red circle there. So it basically learned to steer the plant away for a little bit and then wait for some stiffening to happen and then steer it back towards the target. So this way it didn't like touch the object. But if it wanted to follow a different approach, for example, by maybe alternating the light sources. So the little yellow circles here are actually the two light sources that are present at the grow box. So yeah, so in previous papers we could see such approach, like it keeps alternating the two light sources and then the plant can go up. But in this case, because there is an obstacle, then this is like dangerous, because basically it would hit the obstacle if it didn't actually like try to exploit the stiffening behavior.
But if I remember correctly, here it was sort of known beforehand that the stiffening will happen, and like the model was already sort of prepared for being able to depict this. Can the model also learn it by itself, so without being prepared? Or maybe I'm misinterpreting it.
The model learned that the stiffening happens because it was like because it was trained on these data sets from our experiments, and it figured out, like we didn't like explicitly program it to do that, but it figured out that okay, if you let it grow for a little while at one side, then it's gonna like build some like stiffness at the bottom towards this area.
So this is more my question, like how much was known before and sort of already having the model prepared for it, and how much was sort of found out by the model building approach autonomously.
So yeah, probably. So that was already given in the dataset to be precise.
Okay, but it is possible to figure out physics, for example, for such an approach.
Well, actually, so the controller could figure it out. Like so, besides the model, the LSTM model, there is this evolved controller, and that's the controller that did try and error until it understood how like the dynamics work, and then decided, okay, then I'm gonna exploit this stiffening thing.
Okay, I see we have another comment in the meanwhile from Odin. So do you want to specify what you meant?
So I hand back to Julian.
Thank you.
No, it was only like you were commenting about getting the stiffness. Basically, if you see even in the video, the plant can only grow from the tip. So the stiffness probably won't be part of the game of growth, even if it is branching or not. I mean, if it will be a tree, for example, maybe, but once the plant has grown in one direction, if you change the direction of the light, like in the video, probably won't change much, because the only way of moving is using the water inside, right? So, but that was only like was more for you than a question for him. Sorry.
Yeah, if I'm not mistaken, I think this was also like this makes, of course, the modeling a little bit easier, but of course there's still some some softness left, which might be nice to model. So I guess this is what we're going after. So not everything is immediately stiffened.
Especially with branching.
Yeah.
Okay, thank you,
Yeah.
Julian. I think we are already like 2-3